Back to Precalculus 1 on this wonderful Tuesday afternoon. We're talking about 2.6 today, rational functions. I'm not ready. Yeah, I just didn't flip. There we go. Oh no, that's wrong. So first we define what the rational, and we take a look at its properties, and this will be greatly expanded on in calculus, and it will be used in calculus. And many parts of this lecture will be very important down the line. So please make sure you study this a lot. Not just do problems. Study to understand the concepts and ideas that are presented here. So first of all, the rational function, we can put R of x, is going to be defined as a quotient, division, of two polynomials, where the polynomial in denominator should be different than 0. So we have two polynomials that are divided. And the probably simplest example that we could give in this case is, let's say, f of x is equal to 1 over x. That would be the simplest possible example. Definitely, number 1 is a polynomial because it's just a constant term, but it's a polynomial. And then you have x, which is also a polynomial. Both of them are monomials, but that's fine. And you're dividing those two. Can't be simplified any further. You will be memorizing the graph for this. So you'll be memorizing this graph. And we have x and y. You can immediately see that there is no x-intercept, no y-intercept, because the graph never cuts through either of the two axes. We can see that the domain is negative infinity to 0, united with 0 to infinity, and the range negative infinity to 0, united 0 to infinity. Now we also will see in this lecture two lines. One of them is called vertical asymptote, the other one is called horizontal asymptote, and both of those are represented on this one, but we'll get there. Those are both of the axes that will actually be the asymptotes in this case. But we just want to get these most basic ideas of domain, range, and then the fact that there is no x and y intercept in this particular rational function. Now, just observing the graph, you see that it passes vertical line test, which means that it is a function, right? It is a function. So this is the simplest example of rational function. So you can obtain these rational functions by simply the graphs, right? By simply plotting the points, right? You compute the points, you plug in 1 over 1 is 1, and so on. So you can actually compute and then. But if you know the basic shape and the examples are close enough so you can use the 1.6 transformations, you can draw other graphs by looking at the original one. So let's say you have 1 over x minus 3. So this line moves this way, and now the graph looks like this. Is that correct? Anyone? Yeah? Yeah, nice. All right. It moves to the right, exactly. I was just trying to see if anyone is paying attention. So when you put the minus sign on x, it moves to the right. Yeah, all the people with pen hate me now, right? Yeah, get pencils. So the entire graph shifted 3 units to the right because we had x minus 3. What's happening if I modify this problem as 1 over x plus 3? It's going to go up 3 units. So if this is the original x-axis, we're going to put this line right there, and then we're going to have this. So it goes up. What happens if we are to put, let's say, a minus sign, like this? Yes. So we are going to reflect, which means it's going to look like this. Great. So all of the transformations that you guys learned in 1.6 apply. And this is why I told you that 1.6 is so important, because every function that you ever learn from this course on, and we're going to learn another 2 in chapter 3, and then later you have trig and hyperbolics and all of these other ones, they all obey the rule of 1.6. And then later on for inverses and composition. So those rules are always observed. Great. So we have that. I will just ask you to practice your skills now. So do this one on your own. So draw the graph for that one. How many transformations do you have here? 3 transformations. Which one is the one that I told you should do first? Reflection. So if reflection is one of the multiple transformations, do that one first. I will do this in stages. So this is the default state. Then we are going to reflect that. Then we are going to move it 2 units to the right while reflected. And then the final stage is to move 1 unit down. So we have this one, and then we draw the same shape. So I hope this is how your final graph looks like. Obviously labeled, x-axis labeled, y-axis labeled -1, labeled 2, and it looks something like that. Great. Now is the time for us to define and discuss vertical and horizontal asymptotes, which would be these lines that I've been drawing here, which act as guides for our functions. You are all familiar with the end behavior of the function. Now these asymptotes, so horizontal asymptotes would be considered together with the end behavior, where the vertical asymptotes will be grouped and considered as this local behavior within the interval. So these asymptotes strive towards infinity, and vertical asymptotes are the ones that are literally like a brick wall or a concrete wall that you can't get through, where the horizontal asymptotes you can locally pierce because they are strong only at infinity. So they have to be obeyed far away from, right, let's say the origin. So let's start with the vertical asymptote first. So definition. Vertical asymptote is a line which occurs at a value where denominator of the rational function, of the given rational function, is equal to 0. You know how you can't divide by 0, right? You can't have 0 in denominator. Well, what is the vertical asymptote? Vertical asymptote is that concrete wall, a line that stands at that value, making sure that the function is not crossing there. Because if the function is to cross through that x value, then there will be a solution for something divided by 0. So vertical asymptote occurred earlier in our graph, and that's this line which I drew right there. So that's the line. That's the vertical asymptote. And you see how the graph bends around it. So just to illustrate how this works, let's say you have f of x equals 1 over x, the cheapest possible function. You will set x equal to 0, which will give you that the vertical asymptote is at x equals to 0. Remember that vertical lines have equation x equals a number. We can immediately see this on the graph. So vertical asymptote is right here. And then the graph has to follow it. These vertical asymptotes will show up in many cases. You will have also for trigonometric functions next semester, like tangent and secant, cosecant. They all have vertical asymptotes. These concepts will be actually expanded on in Calculus 1. Now we are kind of careful to exclude certain type of problems that might mess things up with the way the definition is given now. But in your next, well, in the Calculus 1 course, you will know much better definition for vertical asymptote than just words, what we have up there. So now, we would like to see where are these vertical asymptotes. So let's find vertical asymptotes. So let's say that your rational function is given as f of x equals to 3 divided by x squared minus 1. What would you do here? Every time to find the vertical candidates for vertical asymptotes, you will set the denominator equal to 0, and you will solve it. So x minus 1, x plus 1 equals 0. So x is 1, and x is negative 1. So in this case, we have two vertical asymptotes at negative 1 and 1. Vertical lines have equation x equals a number. So if I am to draw this now, I will go and place at negative 1 and positive 1, I will place these lines. And they act as a guide. So the function can come up to these and follow it to positive infinity or negative infinity, depending which way it bends. We're not going to draw the function in. I'm just showing vertical asymptotes in this case.
I have a question.
Yes?
If it's x equals, why do you do it on the y-axis?
What do you mean y-axis? But x must be 1 at all times. So you pick any point. X is always 1 and y is changing values. Great. Let's see how many vertical asymptotes here. How many vertical asymptotes? One? How you come up with 1? I came up with none.
What? Oh, yeah.
Yeah. When you fact it's not even a rational function, huh? This is I know it's a cheat. Right? Not as.
What?
Yes. So if you pay attention, right, if you're careful about this problem, you will see that the numerator factors and then x minus 3 cancels, and you don't have a rational function anymore. No rational function, right? Polynomials do not have asymptotes. Done. No va. Yeah. Now what? Yes, one vertical asymptote at 2. X minus 2 equals to 0. X equals to 2. Boom. Wow. Great. Now I'm going to also state over here in blood that vertical asymptotes are interruptions in the domain, right? Because those are the points at which you have break in the domain because the value cannot be found because the denominator is 0. So vertical asymptotes are interruptions in the domain. So for our good old friend f of x equals 1 over x, which graphed this way and had vertical asymptote at 0, domain was given as negative infinity to 0, union 0 to infinity. So you can see that only a 0, which is the place where we had vertical asymptote, is kicked out. If you pick up any other problem that we did so far, if it has a vertical asymptote, that's where the break is.
So the vertical intercept is basically already stopped. So like if the vertical intercept is like 3.
Yes, which is what I wanted now to bring up. Another example, let's say f of x is equal to, let's go with x over x squared minus 5x plus 6. No, minus 6. No, plus 6 was good. Yeah, plus 6. What's the domain? There is also the part in between the two numbers, because you will interrupt twice, you will have 3 chunks. A chunk in the middle.
So,
2, 3.
so we'll be negative infinity to 0 and then.
No, to 2, and then
3 and then 3. Oh, yeah, you're right.
With two union signs. So we are going to set denominator equal to 0. We are going to factor this over what numbers? X minus 3, very good. And then we have x is 2 and x is 3. So now I'm going to sketch, not the function, I'm just going to show these asymptotes. One is at 2 and one is at 3. So what do I get from this? One is at 2 and one is at 3. I get 3 parts of the domain. We start, so for the domain, I start at negative infinity. I will go up to 2. Then I have to exclude the 2 by using regular parenthesis. Then unite 2, 3, stop again, and then 3 to infinity. So I have 2 interruptions in the domain. Remember that polynomial functions should have domain from negative infinity to positive infinity without any interruptions. Rational functions have the same domain, but it will be cut in multiple pieces, and that amount of cuts is equivalent to amount of the number of the vertical asymptotes. Every vertical asymptote is going to be the cut in the domain, because that is the x value which would make denominator 0, which is bad. So this is what we have for our domain. So vertical asymptotes will be the lines that are obeyed by the function, cannot be crossed by a function, and also interrupt in the domain. And all of that is calculated by denominator equal to 0. Now this will be expanded on in Calculus 1 using limits and other stuff. So there will be more discussion of this in the future coursework. Yes?
How do you graph the whole thing?
We have to first cover horizontal asymptotes, and then we'll have enough guidelines, and then we'll unite vertical asymptotes, horizontal asymptotes, x-intercepts, y-intercepts, and maybe symmetry, maybe computing some of the points to graph the whole thing. So it does take a little bit of work. So let's cover horizontal asymptotes first. So we are memorizing for vertical asymptotes, set denominator equal to 0. Make sure you canceled, obviously, first. Make sure you canceled as much as you can, so we don't get into this situation, for no reason, right? This one does not have vertical asymptote because denominator canceled. There's no denominator. Next part. That line is horrible. Horizontal asymptotes. So what do we have for horizontal asymptotes? Well, horizontal asymptotes will be horizontal lines that the functions follow at infinity. However, they can be pierced. See, vertical asymptote can never be crossed at any point, anywhere. Horizontal asymptotes can be crossed, but they must be obeyed at infinities. So horizontal asymptote is a horizontal line so horizontal asymptote is a horizontal line which function obeys at infinities. It can be crossed locally. So it can be crossed locally. That's very important, so you don't get in trouble. Now, the question is also, how do we get it? And this is where you have to memorize. I know. It's perfectly timed. You will have to memorize 3 cases, and all of the rational functions that you get will fall in one of these 3 cases. So, first of all, let rational function be p of x divided by q of x, where q of x is not 0. So you have a rational function. Further, so and p of x is equal to a x to the n plus dot dot dot. I really don't care for anything else, I just want the leading term. And q of x is equal to b x to the m plus dot dot dot. So that's the leading term. They don't have to have the same coefficients, and they definitely don't have to have the same powers. Actually, you know what? Let me put m on the top one and n on the bottom one, so it's better. The alphabet works that way. So here are the cases. So cases for r of x equals to 8x to the m plus dot 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 divided by b x to the m plus dot dot dot. So if, yeah, I did. I switched them again. Okay, so if n is larger than m, so degree of the leading term in the denominator is larger than the degree of the leading term in the numerator, horizontal asymptote is at y equal 0. If n is equal to m, horizontal asymptote is at y equals a over b. And if n is larger than m, no hop. So if the m larger than n. I keep switching them. All right, so now students general, yes. Over here, ax to the m plus 3 dots. Generally, how students remember this, they say upstairs for numerator, downstairs for denominator. So if the degree upstairs, downstairs is bigger, it's at 0. If they have the same the exponents, it's the ratio front coefficient. And if the upstairs is bigger, no horizontal asymptote. That's technically what it is. Fastest way to remember these. So now, what do we do with the rest? There will be an offshoot of this one. You know what? Let me just write this. M equals n plus 1 slant asymptote. And we'll come back to that one. So let's take a look at this. We go first with our dear friend 1 over x. So 1 is technically x to the 0. This one is x to the 1. So degree m is 0, degree n is 1. M less than n. right, or n bigger than m. So ha at y equals 0 by the rule. And we see that horizontal asymptote clearly. Right there. Y equals 0. This is where it obeys at these ends. Function bends towards the horizontal asymptote and follows horizontal asymptote at those values. F of x equals x minus 3x squared plus 8 divided by, I don't know, x squared plus x minus 1. What can you tell me about this problem? Very good. If you carefully observe, the leading term is buried in the middle. Leading term is always the one with the highest exponent. It doesn't matter where it's written. Not all people are polite, okay? They will put this x squared term, right, the leading term in the middle. That's not, you know, mathematical etiquette or whatever, right? But, you know, some people will do it. It's your job to fish for the leading term and then realize that exponents are the same, which immediately implies ratio of front coefficients, which is -3, so -3 over 1 is -3. So ha at y equal -3. I'm not going to graph the function, I'm just going to graph the asymptote. Horizontal asymptotes are always horizontal lines.
Where's the line coming from?
Coefficient of x squared is 1. So this is the coefficient in denominator, coefficient of x squared. What do you think about this problem?
This path is larger.
Okay.
So we know how.
Yes. Now, do you see that you can actually factor out and cancel x top and bottom? Yep. You can factor out x in the numerator and denominator. My question is, does it change anything? Does it change anything for your horizontal asymptote if you were to do it and cancel? And the answer is no, it doesn't. Cancellation does not impact your horizontal asymptotes because you always cancel the same amount in the numerator and denominator. Would it affect vertical asymptote?
Yes.
Hell yes. There is no vertical asymptote at 0 because that x, which you would set to 0, in the denominator is canceled. So cancellations affect vertical asymptotes. Cancellations do not affect horizontal asymptotes. So even if I'm to cancel out x or factor out x, this will go to x squared, but this will go down to single x. This is still bigger, right? So cancellations do not affect horizontal asymptotes. They only affect vertical asymptotes. So this is still top larger than the bottom, no ha. And I'll put here even if we cancel x, it's still going to stay top larger than the bottom, which means No horizontal asymptote. Yes. Leading degrees.
The
Exponents, right? Leading term, exponents. M and N.
So cancellations only affect horizontal?
the vertical.
Exact.
Now we do a graph.
And now it is time for us to graph some problems. All right. Finally. Let's go. It's something. Why is it immediately crazy problems? Hold on. We'll do something more manageable first. Nah. All right. So let's graph f of x is equal to x minus 3 over x squared minus 4.
What is that set? Graph? Is that
Graph.
what you said?
If it starts with G and then has an R after that,
Okay, but it didn't look like that. It didn't look like that. It looked like the two were connected. That could be. Okay, I got it. But can I see the problem now? Because I needed to zoom out. Okay, that's better. Much better. Thank you. Thanks.
are we good?
Yep.
Awesome.
I was gonna erase it. Come
All right. So, wait, hold on.
Thank you.
Yeah, I get bored while you guys are doing the problem. All right, so what we're going to do here is, there's no reason to record it so live. So,
You need everything.
yeah, so what we are going to do with this one is we are going to find the x-intercept, the y-intercept, by setting x's to 0 and y's to 0, right? That's algebra part. Should be able to solve this equation. And then we are going to look for horizontal asymptotes and vertical asymptotes. So those four you should do right off the bat. So let's go and find x-intercept by setting the entire function to 0, right? X-intercept is where y is 0. So x-intercept is the first one. We go x minus 3 divided by x squared minus 4 equals to 0. How do we solve this equation? I'm sorry?
Multiply by x squared minus
Very good. We cross multiply, so we will multiplying by x squared minus 4. Yep, intermediate algebra.
I thought we said the x squared minus 4 equals to 0, not the whole thing.
That's for vertical asymptotes. We're doing x-intercepts now. So x equals to 3. x equals to 3 is our x-intercept. So we can also write it as 3, 0, right? Because we forced y to be 0 by setting up the entire, right? F of x is y. We know that from lecture 1 in precalculus. So you're setting y to 0, and you solve for x. 3, so 3, 0. X-intercept at 3, 0, that means that the graph will pass through number 3 on x-axis. That's what the x-intercept is. Now we'll go with the y-intercept. You achieve that by setting x to 0. Well, you go into your function, right? Compute f of 0, which is 0 minus 3 over 0 squared minus 4. Positive 3/4, right? So 0 3/4 is the y-intercept. So now we have x-intercept, we have y-intercept. The next are va and ha. Where are the vertical asymptotes? Very good. What do we get? Excellent. So we have two vertical asymptotes at x is equal to 2 and x is equal to negative 2. Nothing canceled. Remember that cancellations affect these, so you have to be careful there. So we have two vertical asymptotes. How about horizontal asymptote? Yay or nay? Y equals 0. Read the blue, right? Now you take all of the information you know and you graph everything you know, and then we'll fit the line in between. So I have vertical asymptotes at negative 2 and 2. I have a horizontal blue asymptote at 0. I have x-intercept at 3. And I have y-intercept at 3/4. So this is information that I have, and I'm supposed to fit in the graph. What to do? So yeah, we have to figure out which way the line goes. Now, let's start. Now, guys, you should really pay attention now. Use all of your brain cells and focus them on this analysis, because this is the tough part. We are going to work first on the first piece of the domain. I'm going to observe that I have a box over here and a separate box below. I do not have any x-intercepts, which means that the line will never cross x-axis. Over here I have it, so it will cross. But on the left, I don't have any x-intercepts, which means the entire function will either be focused here or here. Not on both sides, because they will be stacked on top of each other. Vertical line test will tell us it's not a function. So the only two things that I can draw at this point in time is a piece that looks like this, or the piece looks like this. Not both, one or the other. But these are the only two possibilities that you have. You can't do anything else other than draw one of these two pieces, because they have to bend towards asymptotes. You see how it bends to follow the blue one and it bends to follow the red one. Same thing happens on the top. So now we have to choose which one to keep and which one to erase.
It's the one on the bottom.
How do you know it's one on the bottom?
Because there's not a negative in front of this one.
The fastest way to know whether it's the top or the bottom that you keep or get rid of is to pick a point and compute. So you know that this value is -3, -4, -5, -6. Pick any number. Plug in your original problem, and that will give you either positive or negative y value. If you pick, let's say, -4 for x, and you got negative whatever, then you're keeping this one, because the answer was negative y. If you pick that point and you get the positive value, you're keeping this one and erasing the other one. So you will be computing at -3 or -4 or -5, any of these, to see which one you keep, which one you delete. So our function is x minus 3 divided by no, it's x squared minus 4. I put the wrong one. So this is our function. So now what we have? Test point at -4. So what's f of -4? It's -4 minus 3 divided by -4 squared minus 4. So that's -7 divided by 16 minus 4, 12. That's less than 0. Keep the bottom, erase the top. So the analysis over here was, I'll go from scratch for this piece. This over here is the x axis, which has the horizontal asymptote. You have the vertical asymptote, and you can draw two pieces. No x-intercepts, which means that the function will not cross through x-axis. Now, you pick a value in that region between -∞ and -2, pick a value and plug that value in the original function to figure out whether you are keeping lower part or if it's positive upper part. So that's the analysis for the first, and that's the same analysis that will go for this one, this end here as well. The middle is different. Yes? Yes? No, because two horizontal asymptotes would mean that the function stacks, but you can't have it because of the vertical line test. You can have infinitely many vertical asymptotes. Like the function tangent x I mentioned earlier has infinitely many vertical asymptotes, but at most one horizontal asymptote, never more than one. Yes?
You will always base that graph off.
No, because the denominator can also be, if you have an odd degree, it will preserve the sign. The square kills the sign. But any odd exponent will keep the sign. Then you might have minus or minus is plus, plus or minus is minus, and so on. So just compute to be safe. We got -7/12, that's less than 0, which means keep the bottom part. For those of you still struggling, where is this -7/12? Guys, at -4, which is the value I picked, it gives you the y value that it's right there. That's what it is. Next part is the middle part. You see the point at 3/4. You know that graph goes through that point, but you're not sure how. Look, I'm going to draw a few scenarios and erase them, so pay attention. It can go like this. That's a possibility. It could go the other way. It must pass through the point, right? It could go and bounce off like this, or from below. Now we actually, and I showed you 4. I showed you this one, I showed you that one, I showed you this one, and I showed you this one. Now only one of these is the correct answer at the moment, and I believe it should be straightforward for you to see which one of those 4 is the one that we get to keep. Why you? It can't go through x-axis. In this problem, you are not allowed to pass x-axis because there are no x-intercepts here. You see that? That's the analysis that you always have to have in your head right now. This is the most important skill you're developing right now. You understand that each one of these 3, will pass through S, but you don't have any x-intercepts. It's not allowed, right? The only one that will not pass through x-axis when you draw in this region in the middle is the U shape. So that's the correct one. Anything else, we'll have to see the U shape backwards, passes through these 2 points, and they're not on the x-intercept list, so that's bad. The one that will go from up passes there. The one that comes from the other side, up, passes, right? You have only one x-intercept, and that's the one at 3, so function cannot pass through other values.
So then can you get more than one x-intercept?
Oh yeah, you can have as many x-intercepts as you want, depending on the function. And now, the last part. Now, this one is a tough one. Function could do this. Because it has to follow horizontal asymptotes at infinity. And it must pass through x-intercept. Function could also bounce off and then still bring back. You can do both of those things from the other side. Or like that. So now, the question is which one of these it is. The same trick like we used for the left, we'll use from the right. Pick a number between 2 and 3 and see whether it's positive or negative. Look, it either goes like this or it goes like that. If we get the positive for the number 2 to 3, it's going to go there. If it's negative, it's going to go on the bottom. So let's see. I don't know, 2.5? What's f at 2.5? It's 2.5 minus 3 divided by 2.5 squared minus 4. It's negative. Very good. So, it must look like this. Done deal. We found that for this value here, this x, you have this y.
Why does it go up and then come back down?
Because it has to follow horizontal asymptote to infinity. It can't go and shoot off like this because there is a horizontal asymptote to be followed.
Why don't you just go like this? Here's a point like that.
Like this? It doesn't matter. We really don't know how big the peak is. So you can go with a smaller peak, you can go with a bigger peak.
I just don't know why
That
they're-
information is not unveiled until calculus.
I just don't know why they're. Why not just an abstract? Like, even if I'm holding that number as well.
It's the M1 route, so it passes through, not M2. There's just so much. At one time, there's just so much information that it's no matter which problem I pick, it's going to be bad.
I just have a question. Why is there a peak at all? Like, why does it have the wrong?
I'm sorry?
Why does it have a peak? Like, that doesn't make sense.
But how else would you bend back to x-axis?
Like this. Like, there's a point.
You want to go like this.
Yeah.
That's the same thing, except it doesn't peak as fast. Doesn't matter. There's still, look, this is the maximum, right? And here's the maximum for this one. It doesn't matter. You can go like this.
It doesn't matter.
We don't have the information until calculus to tell where this peak is. Calculus is going to give us that peak.
Oh, wait. So can we just draw it like this?
No, you have to bend back.
Oh, we have been.
You have to bend back to x-axis because you have the horizontal asymptote there. Horizontal asymptote.
Oh, okay.
What if there's like just no peak at all, so it just goes through horizontal, and then just kind of just goes straight. Not there's like a
There is horizontal asymptotes. They have to
You
have
have
the
to go
point.
back to horizontal asymptote. Horizontal asymptote. I know. I mean, you get enough. Asymptotes are like that at all times. Two smacks and. All right. That's all. Horizontal and vertical, both of them. No exceptions. All right. So. Such is it's difficult life of functions. They have to follow rules. I'm going to just cut and paste the problem from the textbook 26. Age of x, whether it's f, h, g, doesn't really matter. They give you this in factored form already because they really don't want you to strain your back trying to factor this. Graph it, find the asymptotes, intercepts, just do the whole thing. Do the whole thing. No, because then vertical line text is not a function. One or the other, right? One or the other. No, they could be the same, they could be opposite. That depends on the number of x squared, x over x squared, x squared over x squared. The curse of this section, man. You cannot memorize the problems here. This is the section. This is the section where the variety and number of combinations you can get is insane. And if you're trying to remember this case by case basis, your head is just going to explode. You actually have to get the concepts.
Oh, wait. But how did you get the x and y intercept again?
Set x equal to 0 for y intercept
Oh,
and
just
y
the
equal to
regular. Oh. Okay. I was like, I thought you did this.
Yeah. Throw this out. problem. All right, let's
It
do
is
this
a
problem
Why
together.
didn't you give us one that was so bad?
It looks so easy, right?
It looked easy.
Yeah, I know. You cancel those x's and everything is done, right? Yeah.
Oh. 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 I want to learn. So.
Boom. Right. Now, it is very important to note that x is different than 0, right? Because at 0, we are going to have a hole in a graph. I know. So let's go with the x-intercept. Where is the x-intercept? There is no x-intercept, right?
Because there's no fraction.
Exactly. So x over x minus 3 equals to 0, right? These guys cancel, and you get 1 equal to 0. Makes no sense. No x-intercept. Perfect. Moving along. Y-intercept. We have 1 over negative 3. Well, 0 minus 3, right, is equal to negative 1/3. So we have 0, negative 1/3 for y-intercept. Great. How about va?
Hold on, I'm not there yet.
3. X is canceled, and because x is canceled,
No
x minus 3 equal to 0, x equals 3, va. And how about ha?
No.
Yes?
Oh, there's the bottom one.
Yes, the denominator has a larger exponent, which means
No ha.
y equals 0.
Why? I don't even know where omega is. How do you get from?
Great. So now we're going to graph this. First of all, there is a hole at 0, 0. We are not allowed to have a function value there.
Wait, how do you know there's a hole?
Because x in the denominator and the numerator canceled, there are no x-intercepts, but you still can't have x to be 0. If you look at the original function, before we canceled, you have x in the denominator. You can't plug 0 in, but it's not vertical asymptote at the same time. So it's just a hole in the graph. We have vertical asymptote at 3. You have a horizontal asymptote at 0. And you have the y-intercept at negative 1/3.
You have not labeled your graph.
Okay. X is not allowed to be 0. That means that this 1/3 is the open circle. The function comes in, bends down, because you only have two choices. You have a choice going this way and a choice going that way. Those are the two choices. Now, when you do have a point, either x-intercept or the y-intercept, it is clear which one it is. Now, on the other side, we have a choice between this and that. We're going to make that easy once we compute one of the points. So compute at, let's say, 4. Right? You compute f of 4, or age of 4, actually. So that's going to be 4 over 4, and then 4 minus 3, which is equal to 1. Right? These guys cancel. So, there we go. So this concept of a whole is a little bit off for now, but you will get used to it. Yes? 4 minus 3, yes, the function. Function is 3. Yes?
What are you saying? Okay.
I have no clue what she said because I couldn't hear.
She said, could you pick one that looks hard so it's actually easy? And I said, if it looks hard, it's gonna look hard.
So to make some people happy here, f of x equals to
Oh, can no, can cancel too. What the? I honestly I didn't hear it. She might walk in, I'll walk out.
They're gonna take a photo. Really? Really? weak.
I used to do that and look, it works like again.
I know.
See?
Both of them. I just work.
I have a question. I get confused in the horizontal.
You just look at the exponents. So exponents on the top is zero. There's no x. Exponent x. So 0 over 2. So bottom bigger.
Over 2. You're wrong.
I'll give you a few more moments to enjoy.
Someone sprayed cologne. To be honest, it smells good. So whoever sprayed cologne, congrats. It smells in here too.
Yes.
Smells good. Good job. Damn. What is that?
Shall we look at this together? You have the graph so you can follow along?
Let's do this. I'm ready. We got like 2 minutes.
What clock are you looking
4
at?
minutes.
Is that's the Apple time, right?
I just guessed, but now I know it's over. Let's go though. We
All
got
right.
2 and then 2 more, so let's go. 2.
All right. So, x-intercept is where we set the entire equation equal to 0 to function. When we cross multiply, we get -2 is equal to 0, which is not true statement. So no x-intercept. That means that the function, the line that we draw, will never cross x-axis. y-intercept, set x equal to 0. So we have negative 2 over 0 minus 2. And what do we get? Okay. So that would be 0, 1 for the y-intercept. So we do have that one. For vertical asymptote, we will set x squared minus x minus 2 equal to 0, which factors over x minus 2, x plus 1. X is 2, x is negative 1, and those are our vertical asymptotes. For horizontal asymptote, there's usually some confusion here. Guys, you have to memorize those three cases. So for horizontal asymptote, we are going to have, no coughing, we have negative 2 over x squared minus x minus 2. If you observe the degree on the numerator, you can add 1, right? Which is x to the 0. So m is equal to 0, n is equal to 2, so m less than n, which means y equals 0, horizontal asymptote. So that's usually the confusion, and mainly because you didn't learn the cases. That's the mainly why the confusion is there. So, you know, if you learn this, there should be less confusion on Thursday. So now I have all of the information that I can find. I have vertical asymptotes at 2 and negative 1. And horizontal asymptote at 0. And I do have the y-intercept at 1. So what have we learned so far? It's $1 more for the fundraising. So now we know that we can have either one of these two here. We plug in a value, let's say negative 2, in the problem. And we get less than, which means we keep the bottom piece. Then we're looking at the middle, and clearly there are no x-intercepts. If there are no x-intercepts, then the U-shape has to look up. Because no x-intercepts means it is not going to go through x-axis. The only shape that fits that description is the U-shape going up, because it has to follow vertical asymptotes on these parts. Now, the last piece is this. Again, either one or the other, right? And we compute again. So let's compute at 3, and we're done. So what's f of 3? Negative 2, 3 squared minus 3 minus 2. That's going to be negative 2 divided by 9 minus 5 is 4. Again negative, so it's this piece. So both of these kept the lower portion. As you compute, so you compute single point. And that's it. We still have to talk about slant asymptote. So we'll finish that next class. I will do 2 examples. I'll add to this. This is when the degree and the numerator is by 1 larger than degree in the denominator. So we'll deal with that on Thursday. See you all Thursday.